about to start learning about chemical equations, what they are, how to classify them, how to balance them, how to predict products of chemical equations. But in order to do well in this unit, you have to first learn some things that we, in this class at least, learned prior to this, like how to balance formulas. Okay, so chemical equations is what this unit of instruction is about. And there are, just like with chemical compounds, where we had 4 different categories of chemical compounds, we've got different categories of chemical equations. And you've got to be able to classify chemical reactions. And mainly you classify those chemical reactions by the equation, at least you do in this class. So there's 1, 2, 3, 4 major categories and 1 subcategory, I believe it is, okay? Well, actually 5 categories and 1 subcategory. So the first chemical equation category is a synthesis reaction. Synthesis reaction. And in a synthesis reaction, 2 or more chemicals are being combined into 1. So if my chemical, the first chemical is A, and the second chemical is B, then you could think about this in really simplified terms as combining A and B into AB. Now the problem is that this has to be balanced. You can't just write a chemical and say, oh, that's it. You can't just stick them together and that's done. That's not the way it works. You have to balance the formula when you're done. Okay? Then the opposite of synthesis is called decomposition. And in decomposition, 1 chemical is separating into 2 or more. And so the super simplified way of illustrating that is you've got a chemical that's made of A and B, which I'm not showing as being balanced. Okay, sometimes there are subscripts to go in here that indicate how many A's and how many B's there are. And we'll get A plus B as separate things. And again, we haven't balanced that either. There could be coefficients out here or subscripts that go along with that. So synthesis and decomposition are 2 sides of the same coin. One is the inverse of the other. Synthesis is putting things together, decomposition is breaking them apart. Alright, then we have single replacement. Also called single displacement. And I actually prefer the second term because I think it's more descriptive of what's going on. Okay? And in single displacement, 1 chemical displaces something that it is like in a compound. So for something like that, we might have A here. A is 1 chemical. And we have a compound made of B and C. And I've kind of color-coded this to show you how A and B are kind of alike each other, okay? In some way, they're alike. And we'll talk about what that means in a moment. And so in a single displacement reaction, A can displace B. All right? And the result is that we get, over here on this side, AC and that kicks out B to be by itself. Now it might be that the compound or the part of the compound that's being displaced is not on the front, it's on the back. In which case we would have this, A plus B, and now C is like A, all right, in some fashion. And in this case, A is going to kick out C, and we end up with, I should have made that a red letter A instead of black letter A. And that's going to leave C by itself over here. So this right here, we have the front part of the compound being displaced. This is metals displacing metals or hydrogen. Okay, this one down here is when we have halogens displacing halogens. Now to remind you, so that we're clear about where we find those different types of chemicals, you get out your periodic table. Boy, have you begun to realize you've got to have your periodic table every day? I mean, that's just like the most important tool a chemist has. So if you don't have out your test references and have out your periodic table, you need to get that out. Okay, and let's just be clear, you can visually reference this, and the more you visually reference things, the more you're going to be able to visually reference it on a test to be able to use it properly. Okay, when you don't use the tools, you don't know how to use the tools. You think you do. Okay, if I'm a carpenter, I use a hammer a lot. Okay, well, there's a right way to hold a hammer and a wrong way to hold a hammer. Did you realize that?
Yes.
You can wear, you've done carpentry before? There you go. So if you're holding the hammer in the wrong way, you're wearing out your arm, man. You're going to be so sore after a day of working with a hammer, you can't stand it. But if you hold it the right way, where it's properly balanced, you know, it's like an extension of your arm, and it works out really well. I mean, that's a simple tool. There are lots of tools like that. You learn to use it right, or you kill yourself, basically, almost. You know, you don't really kill yourself, although I suppose you can with certain tools. Okay. Anyway, certain large power tools, you know, you kill yourself, right, if you don't use them right. All right. So metals are located over here. Non-metals over here. The dividing line, or the stair step is a line. It's kind of a crooked line. Metals over here. Non-metals over here. Halogens are everything in this column right here, next to the last column on the right, number 17 or 7A. Everybody understand? That's what halogens are. So you need to know where those are. We did all that in Unit 1. We talked about where the different regions of the periodic table are because it comes back. We need it again. Okay, well, here we need it. All right. So that's single replacement or single displacement. Now we're going to have double replacement. And I don't use double displacement. I pretty much use double replacement here. So this is a super simplified reference to this, okay? We haven't balanced this formula or balanced this compound formula, this one or this one. Those things have to be balanced, all right? You might have subscripts here, or it might be that C is not just one element, but a couple of elements making a polyatomic ion, all right? So this is a super simplified representation of what's going on, okay? Now then, double replacement means that I've got a couple of chemicals, and I'm going to color code them again to kind of help you out. So this is A and B and C and D. All right, so B and D are kind of alike in some way, and A and C are alike in some way. And almost always, though not every single time, almost always, these are ionic compounds or acids and bases. Ionic compounds or acids and bases. Okay? And so the front part of the compound formula is going to be some kind of positive ion, or hydrogen if it's an acid. Okay? The back part is going to be some kind of negative ion. So we have an ionic compound here, or acid, an ionic compound here, or acid, and bases are also ionic compounds as well, almost always. Okay? And so in this case, then A and C are going to switch out. Okay? A and C are going to switch out, or you could say B and D are switching out. Any way you go about it, you have these two things switching around. Okay? We just went through homecoming here, and let's just say, for example, if we were trying to put this in terms of people and couples, this is couple A and couple B. Okay? They go to the prom, all right? And when they leave, A doesn't leave with his date. He leaves with this other guy's date here. Okay? Or maybe she left with the other girl's date. I don't know. Okay, maybe it might be sexist to say the guy leaves with a different date. All right? All right, so A is going to join up with D. That kind of sounds weird, doesn't it?
Not at all.
Not at all? Yeah, a guy would say that. That's okay. Yep. All right. All right? So, notice that A always stays in the front, and C always stays in the front. Okay? Metals or positive ions are always written first. Positive ions are always written first. You don't write the metal part of a compound formula last. You don't write the hydrogen, because that's the positive part of an acid formula. You don't write that last. You always write it first, at least in non-organic chemistry. All right, so that's a simple representation of what double replacement looks like. And I didn't give a definition for it, so I guess I'll write this one below. This is where the positive part of one ionic compound or acid switches places. The positive part of another ionic compound or acid. Okay? So acid, base, or neutralization are a subcategory of double replacement. Now, so here's why I want to make that really clear that it's a subcategory. If I give you an acid-base reaction, you have to classify it two ways. It's not enough to classify it one way. Okay? If I give you an acid-base reaction, you have to classify, or a neutralization reaction, you have to classify that as double replacement and acid-base, or double replacement and neutralization. Okay, so you have to know and tell me that it falls into two different categories, or falls into a subcategory of acid-base. Double replacement. So double replacement then looks like this. Acid-base is going to look similar to that, only instead of using A, I'm going to use H for hydrogens. Okay, and instead of the base like D, we could use OH, because most of the strong bases anyway, most of the bases we work with start out like that. Let's do it this way. So let's put H with A. Okay, H with A. All right? And this is a general formula for all acids, okay? And the reason it's written like this is you have a hydrogen ion and some kind of anion. Please remember, the definition of an anion is a negatively charged ion. Okay? A negatively charged ion is an anion. Okay? And then we're going to put that together with B and OH. Now, not all acid-base reactions are so simple as this. And we have a whole unit on acids and bases later in the year. But if we join these two together, when we have this kind of acid base, and there's a name for this, excuse me, name for the person who came up with this idea about the definition of acids and bases. His name is Arrhenius. Okay, this is an Arrhenius acid-base reaction. Because what we have here is a hydrogen ion joining up with a hydroxide ion, and we make water. Reaction. That's just shorthand for reaction, RXN. All right, so we know that when we react an Arrhenius acid and an Arrhenius base, when we react an Arrhenius acid and an Arrhenius base, we're going to get two things. We're going to get water and some kind of salt. So this is a new definition of a salt. Okay, we could define a salt then, as most chemists do. A salt is the product of an Arrhenius acid-base reaction other than water. A salt is the product of an Arrhenius acid-base reaction other than water. Arrhenius. Okay, you need to know that's what a salt is. So that means there's a lot more salts besides NaCl, sodium chloride. You can go to the grocery store, the drugstore, Walmart, and buy Epsom salts. Okay, and that happens to be magnesium sulfate, which is the product of an Arrhenius acid-base reaction other than water. If I take sulfuric acid and react it with milk of magnesia, magnesium hydroxide, I'll get Epsom salts. Okay, so milk of magnesia is basically a base. It's just magnesium hydroxide, okay, with a little water in there. All right. So this is neutralization because what happens is the acid and base are neutralized by each other. Acids neutralize bases. Bases neutralize acids. And we get a salt and water, which is, they don't always have a neutral pH, but they have a much lower pH than you started with anyway. Much, at least, lower, higher than this and lower than that. Okay? Much closer to 7 when you do that. Not all bases, not all salts will give you a neutral pH. All right? Sometimes they're going to be a little more acidic or a little more basic. And we won't get into that until later when we get to the acids and bases. Everybody got that? All right then. And then we've got combustion. And we're familiar with combustion. We've done combustion in here before. Okay? Combustion reactions always have a fuel always have oxygen as the reactants. And when we're done with the kind of combustion reactions we're going to deal with in here, not all combustion reactions fit this definition. We're just going to stick with really simple combustion reactions. Okay? There are other combustion reactions besides the ones we're going to be talking about in here. And those combustion reactions you'll learn about perhaps in later classes. But in this class, the only kind of combustion reaction we'll be dealing with will have some kind of hydrocarbon fuel. So our fuel is going to be some kind of hydrocarbon. And you should know what a hydrocarbon is because we've worked with those before. That's what we named when we did organic chemicals in the previous unit. A hydrocarbon fuel and oxygen. Oxygen is always going to be O2. We're always going to get as a product then carbon dioxide. and we're always going to get water, but because of the heat of a combustion reaction, it doesn't come out as water, not as liquid water anyway. It does come out as water, but not liquid water. It comes out as steam. So it comes out as a gas. Okay? All right, so we're going to have carbon dioxide. I'm sorry, we're going to have a fuel, not carbon dioxide. Any fuel, and our fuel is going to be a hydrocarbon, so it's going to be carbon and hydrogen. All right, and those are the things we named in our organic chemicals in the previous unit. Okay, so some kind of carbon and hydrogen compound. The number of carbons and the number of hydrogens doesn't really matter. We can have any number of carbons and any number of hydrogens that will give us a reasonable formula. So that's why I put C sub X, H sub Y. And then we're going to put it together with oxygen, O2. And oxygen is always going to be in the form of a gas. So we're going to say G here for gas in parentheses. And we're always going to get carbon dioxide. And at the temperatures and pressures we're working with, carbon dioxide is also going to be a gas. And because of the heat generated in the reaction, the water is also going to come out as a gas. Okay? That's our general formula then for a combustion reaction. So anytime you have a hydrocarbon and oxygen, you always get these products. This is the easiest chemical equation or reaction to predict products for, because they're always the same. All you have to do is identify what kind of reactant you have, hydrocarbon and oxygen, and you always know what the product's going to be. You don't have to do any balancing of formulas. It's always H2O and CO2 every time. Okay? So those are our 5 categories. Okay? So let's write down a few chemical equations and see if we can classify those then. All right? Everybody still working on that? All right, let's define what AQ is. AQ means aqueous, dissolved in water. AQ means aqueous, and that means something is dissolved in water. Okay? So this is aqueous, dissolved in water. That's aqueous, dissolved in water. Okay? This is going to be dissolved in water. All right? So I want you to write underneath this equation what you think the classification of this equation is. Okay? Write what you think the classification of this equation is, and then we'll come back and revisit that and see how everybody did. You can talk to a neighbor if you want to try to help figure it out.
Do we have to have those little parentheses for that?
Yeah, these are all G's. I'm sorry.
Or G's?
Yeah, G's.
Do we have to have one?
Yep, you have to identify what the physical state of the gas is, or the physical state of the species is. In this case, they're all gases. Hmm?
Yeah, I got a lot of people wearing theirs today.
Let's see, where'd I put a pen?
Oh, I have a pen.
There it is. Here, why don't you fill it out? I'll sign it for you, okay? Who's still working on this? Raise your hand if you are. Okay. What? Well, there's a nice program if you're, if you're taking pictures and notes from time to time. I wouldn't recommend doing it all the time. That's not a good idea.
No, I'm learning.
I got you. But there's a nice program called Cam Scanner. It goes on your phone, and what it'll do is it'll turn your notes that you take pictures of, it'll turn it into a PDF file, which is much easier to keep up with and it's easier to see. It'll even adjust the contrast on it so it's easier to read the notes.
I used to do that.
I use it all the time.
Like if I can't send something in an email or
Mm-hmm.
something like that, I just take a picture and email it off.
Yep. All right, there you go. All right, who's still working on this? Anybody? Okay then. Cortland, what kind of equation is this? Huh? Synthesis. Okay, we're taking two things and making it into one. Again, I don't have my notes here to show you. Okay. So synthesis was the first example that I showed you here. We have one part, one chemical, joining it with a second chemical to make a combined chemical. That's what we have here. Okay. Now these are really simple classifications because there are a lot of equations where sometimes you have more than one thing going on. Okay. So it's not always just one, real simple like that. And there are really large chemicals that you synthesize. If I'm making a polymer, so you're sitting on polymers. Okay. Your clothing's a polymer. Your plastic seat you're sitting in on your desk is a polymer. And what those are is you have a lot of mers, which are individual little molecules, poly joined together into a really long, really long chain of molecules. Thousands and thousands of these molecules linked together to make one big molecule. Okay? And that's synthesis. Even though it's not just two things, but hundreds and hundreds and thousands of these things linked together to make them. All right? Okay.
So the chair is a molecule?
Huh?
So the chair is a molecule?
No, your chair is made of a number of molecules. So what you have are a bunch of these long string-like chains of molecules called a polymer. And those polymers then sit next to each other and kind of stick together on the sides. And that's what makes the plastic. Sometimes there's some cross-linking, some actual bonding between one of these chains and the next one. Okay? But a lot of times they're just sticking together too. Okay? And we'll talk about how that happens later in the semester when we talk about how polar molecules stick together some. And there are lots and lots of interactions between molecules that we don't really get into in high school. Okay, so this is a synthesis reaction. Let's look at this one. Okay, I haven't balanced this. Sure, that'd be a good idea if you balanced it. I'll let you balance it if you can't already see what I wrote down here. That's fine if you've already written the classification. Balancing, we're going to use a new system that you may not be familiar with in here. It's called atom inventory. And that's what I expect you to use every time you balance an equation in here. Even though sometimes it's not really very complex, I want you to practice with it so that you get good at it, and when the time comes to use it in more complex situations, you'll be able to. All right, so I went ahead and balanced the equation, and we got carbon and hydrogen. That's 3 carbons. That must be methylpropane, okay? And we got oxygen here. And what kind of reaction is this? Huh? Combustion. And since we, in this particular class, this particular semester, took our units of instruction out of order in order to do our ice cream lab while it was still warm, we've already dealt with combustion reactions. That should be easy for you. Okay, you should recognize combustion reactions because we had a whole unit on it on thermochemistry where there was a lot of combustion reactions involved. Okay, let's try another one then. How about we do this? And let's see, you used this chemical on Saturday.
Yay.
How'd it go Saturday,
I thought it went pretty well. What do you guys think?
Was there some cool demonstrations?
Oh yeah, they did a really cool demonstration.
Whose was the best?
No.
Whose was the best?
Yeah, the whole thing. What school?
Well, since we were the only high school there, we were the best.
The only high school, right?
Yeah, we're the only high school there.
Why?
All right, Olivia, what kind of equation is this? What kind of reaction is it? Decomposition. Yeah, I thought since Mallory and Taylor did this stuff on
Taylor.
huh?
Taylor.
What'd I say?
Taylor.
Oh, yeah, no, I'm sorry, it wasn't Taylor. Jenna did this on Saturday. Did this reaction on Saturday that I shouldn't have called on them. That would be unfair. Y'all had this done already, right? You knew this, right? Yeah. Okay. All right. Only they used a catalyst in here. We talked about catalyst in Unit 10, right? When we took it out of order. And what was your catalyst to make this reaction go really fast?
Iodine, the potassium iodide.
Potassium iodide. And so they got the reaction going really, really fast. And maybe as a demonstration, we'll let them do their chemical demonstration in here for you guys. Okay? How about, you want to plan on doing it tomorrow? Can you guys come in just a little bit early to get your stuff set up tomorrow?
Tomorrow?
Yep.
Yeah.
For the class?
Like
No?
5 minutes early or like 30 minutes early?
Well, enough to get everything out and get everything set up.
Maybe that's not-
All right. Well, you decide. If you don't get it done before class starts, we won't do the demonstration. All right? Okay, here's another reaction for you guys to classify, and we'll move on to something else then, okay? Let's see here. Get my references out myself. All right, let's classify this reaction. All right, Bryson, what we got here? Single replacement. Okay. Oh, can I have my other page of notes back? No, hold on. I've got it right here. Never mind. Forget it. It's right here. Single replacement or single displacement. Okay. I had to fold it down to see it, so you see it all together. But we have this front part of this chemical is being displaced by that one. Okay. So it looks like this first one here. This front part is kicking out that part. A is joining up with C, and what we have here is kind of like A joining up with C here to make magnesium chloride, magnesium 2 chloride, or manganese. I said magnesium. Man, that's a mistake that beginning students like you guys make. Magnesium is replacing iron and making magnesium 2 chloride. Okay? All right. That's a classification. Now, before you can do anything else with chemical equations, you have to classify it. Okay? You can balance an equation without classifying it, but you can't predict the products of a reaction without classifying it. Okay? So we've got to do a couple more things here. One thing, we've got to learn to balance equations using this atom inventory system. And another thing we've got to do is to learn to predict the products of reactions. I want to go through balancing equations first, and then we'll get to predicting the products of reactions. So there's of the equations we dealt with here in our notes, you have to be able to predict the products of double replacement, acid-base double replacement, single replacement, and combustion reactions. I don't make you predict the products of decomposition or synthesis, although from a lot of those it's not so hard to do. But it's not a for sure thing. With double replacement, single replacement, acid-base double replacement, and combustion, you can always get the right product. And we're going to practice that a lot in here. Okay, so all that stuff we learned about balancing formulas in the last unit, coming back to this unit. Okay, you're going to have to do that as well. All right, let's talk about balancing equations using an atom inventory system. Atom inventory. Well, my writing doesn't look so good today. All right. Here's how this is going to work. First thing you're going to do is to make a vertical list of all of the elements in the compound. Okay? A vertical list. So we're going to take lead. Then we're going to take silver. I'm making it vertical like this. We're going to take chlorine and oxygen. There's our vertical list. Okay? Then we're going to build a kind of grid here. Kind of a really super simplified sort of spreadsheet. So when you take an inventory in a store, you have a bunch of things listed vertically, and then you've got stuff written out to the right where you put in the numbers. You count them off and put them in there. This is kind of like that. Okay, it's kind of it's a chart of sorts. Okay, and this is what it looks like. Now, what I've done is to arrange this atom inventory so this line right here is underneath the arrow. Okay, so this line right here is underneath the arrow. Then the next step is to count all of the elements, all of the atoms we have in each element category. Okay, so I've got a list of elements. The reason that line's right up under this arrow is because I want to count all the elements on this side and put that in here, count all the elements on this side and put it over here on that side. So how many leads do we have so far? 1. How many silvers do we have?
1.
Just 1. How many chlorines do we have?
1.
How many oxygens on the left-hand side do we have?
3.
3. On the right-hand side, how many leads do we have right now?
1.
1. How many silvers do we have right now?
1.
How many chlorines do we have?
1.
Not 1.
2.
Yes, this 2 outside the parentheses means everything inside is multiplied by 2. So we have 2 chlorines. How many oxygens do we have? 6. Okay? So we don't have the same number of elements on both sides. And if we don't balance this equation, then we're violating one of the thermodynamic laws of the universe. Okay? We've created matter. And we can't create matter. Okay? That's not possible. In chemistry, you don't create or destroy matter. Okay? This is called the law of conservation of mass. All right? Or the law of conservation of matter. So do you remember the law of conservation of matter? Okay? If you don't remember the law of conservation of matter from physical science, because you should have been taught that in physical science, but if you don't, let me give it to you now so that you can remember it and write it down. Okay? Even if you're not sure about it, write it down. Okay? The law of conservation of matter. The law of conservation of matter. In a chemical reaction, matter is neither created or destroyed. In a chemical reaction, matter is neither created or destroyed. Okay? Now that doesn't mean that matter can't be created or destroyed. It means that in chemical reactions they're not created or destroyed. So when Le Chatelier I said not Le Chatelier. What is his name? Um, There's another Frenchman. For some reason, it just like completely escaped me, and this is so important. I'm sick today. He's the father of chemistry, they call him. He's the guy who coined the term chemistry. Man, I'll think of it later, pop in my head. But anyway, this was like in our American Revolution, at about the same time. This is when this guy came up with this. Okay, he figured all this out, that you can't destroy or create matter. Of course, later on we figure out around the turn of between 1800s to 1900s, around in that area, we began to realize, wait a minute, there's some matter being destroyed or created here. Okay, and we realize as time goes along that you can destroy matter. That's the idea behind a nuclear power plant or a nuclear bomb. Okay, you're actually destroying matter, changing matter from matter and energy. So now the big upshot of all that, the big law of all that is you can't create or destroy mass energy, okay, or matter energy. Okay, matter can be changed to energy. Energy can be changed to matter, but you can't destroy the matter energy in the universe. Okay, that's consistent or constant. Okay. So now, once you have balanced formulas, so these are balanced formulas, okay? Once you have balanced formulas, you can't change the subscripts inside the formula. So we can't change this 2 to a 3 to balance the equation. We can't put a 2 inside here to even out the number of chlorines and oxygens. The only way you can balance an equation, once the formulas are balanced, that's why we dealt with formulas first in the last unit. Once the formulas are balanced, you've got to leave them alone, okay? So we can't change the formula, but we can use coefficients to multiply the number of those formula units. So I can't change the formula, but I can put a coefficient 2 out in front to change the number of them I have. Does that make sense? You with me? Okay, so I can put a big 2 out in front here to change the number of those. But in doing so, I've changed 3 of the things in this list. How many silvers do I now have? How many chlorines do I now have? 2 chlorines. That coefficient in front changes and multiplies everything in that formula, because we're taking this formula unit and saying instead of 1 of those, we've got 2 of them. Okay? And so how many chlorines do I now have? Mariah, how many oxygens do I now have out Mariah? Over here on this side of the equation, left side of the equation, how many oxygens do I now have, having put that 2 in front of the formula? 6. All right, we're almost done. We've got the chlorines balanced and the oxygens balanced, but what's not balanced? Huh? Silver's not balanced. Okay? So Jenna, what can I do to the right-hand side of the equation to balance the number of silvers? Where?
In front of silver.
Okay, so a 2 goes there. This gets canceled out and we put a 2 there. And that's an atom inventory. Everything's balanced. Okay? Now, anybody here from Missouri? No? Well, I'm from Missouri.
You are?
Not really. But, like all Missourians, I expect you to show me that the equation is balanced. And this is how you show me. Okay? Got that?
I have a question.
Yes.
What does that have to do with Missouri?
Oh, look it up. Thank you for asking the question. All right. Let's balance another equation. What do you
Do I
say?
get extra credit if I look it up in grades?
No, not for that. That's not really chemistry. But anyway, all right, let's move on. All right, so what products are we going to have for this reaction here? How about it, Akira? What kind of products will we have for this reaction? It's the easiest one to predict the products for. I said it a while ago. I said it's the easiest kind of equation to predict the products for. So since we have this kind of equation, what products are we always going to have? Huh? A 2? No, I mean, what are the chemical products? What are the chemical compounds or elements I'll put on the other side of the equation.
Carbon, hydrogen, oxygen.
These are reactants on the left. These are products on the right. What products go over here?
Same as
Carbon, hydrogen, and oxygen.
Okay, those are the elements. How do I put them? Thank you. Okay. Anytime you have a fuel, this is a hydrocarbon fuel. This is oxygen. We're going to have carbon dioxide and water. Okay. So now you guys can attempt to balance this equation. Okay. See if you can work it out. And you're welcome to work with a partner. All right. Okay. I kind of expect you to get stuck on oxygen because I'm going to give you a little tip to get past being stuck. Okay. All right. So our first thing is to do is to write out our atom inventory grid or chart here. So we got this, and this is kind of appropriate this time of year because a lot of people are sneezing this time of year from colds. Say what? What? Okay. So how many carbons do I have to start with? Hydrogens, oxygen. On this side, 1, 2, 3. Always starts out 1, 2, 3. Huh?
Yeah, the other side.
What?
You got it too. Three.
Yeah, 1, 2, 3. That's what I was saying. 1, 2, 3. All right. So let's see. What are we going to start with to try and balance this out?
Start with carbon.
Start with carbon. Put a 2 here. That's going to give us 2 carbons on this side, but it's going to change the number of oxygens. So the number of oxygens we now have, or 2 times 2 is 4 plus 1. I got 5 oxygens. All right. We need to change the number of hydrogens. I've got 6 over here. How do I get 6 over here? 3. Which changes this to 6, but it also changes the number of oxygens. Okay. 4 plus 3 equals 7. Okay. All right. So I've got an odd number of oxygens on one side and an even number on the other. Solving this problem is really simple. You're going to go one of those Homer Simpson moments. You can go, duh, when I do this for you. Okay. It's going to be really simple. I'm going to go through and multiply all the coefficients in front of all the species except oxygen by 2. Put a 2 here. Change this to 4. Change this to 6. Multiply all the coefficients in front of all the species except in front of oxygen by 2. And then recount. Well, I have to multiply everything by 2 here. This is 2, 12. I'm not going to do anything with that because I didn't put a coefficient there. This becomes 4. This becomes 12. And this becomes 14. Now balancing the oxygen is going to be simple, isn't it?
C would be 4. Top left is carbon. It'd be 4
Oh, I'm sorry, you're right, that's 4. All right, so what's the number of oxygens now? Got to be on the left side here. 7 here. That makes 14. Okay? That's pretty simple, isn't it? That fixes it. Okay? All right. Let's try something else here. How about we do, so that was single replacement. Let's do a double replacement reaction. Where's my, here we go. All right, I know you can hardly read that over there because I kind of messed it up, but that's a 3 outside the parentheses. Is it more like a 3 now? Well, I don't know if I'm making it any better or any worse. It is a 3. It's supposed to be. You can tell that's a 3 now? All right. Classify and balance. The math is not hard. It's just a lot of the same kind of math you've been doing since what? 2nd grade? All right. It's just adding and subtracting here, okay? A little multiplication involved, okay? All right. So the 3 outside the parentheses here gives us 3 carbons. 3 outside the parentheses also gives us 9 oxygens, 2 irons, 1 chlorine. So I'm going to start with the sodium. Now look, here's a tip, guys. Here's a little tip. Save oxygen for last, always. Balance oxygen after everything else is done. Okay? Most of the time when you save oxygen for last, it works out. You don't have to worry about oxygen. And if you have both oxygen and hydrogen, then save hydrogen for next to last. Okay? Always balance. Doesn't mean you have to write it last. It just means you balance it last. Okay. So we're going to change the, we're going to put a coefficient 2 in front of this. It's going to change the number of sodiums to 2. The number of chlorines is going to change to 2. Well, guess what? 2 is not going to work out because I got 3 on this side. So how do I fix that? Well, I need to change this to something else, and this is something else. What am I going to change it to? How about I put a 2 here and change that to what? Well, if I change this to 2, that gives us 2 irons and gives us 6 chlorines. Why do I get this to be 6 chlorines over here? 6. And that's going to change the number of sodiums to 6 and the number of chlorines to 6. Now I need to go back over here because now I've got only 2 sodiums. How do I change that? Put 3 in front of that. That gives us 6 sodiums, and it changes our chlorines to, carbons to 3, and our oxygens to what? Hey, everything's balanced. You just kind of keep going back and forth until everything works out. And you might choose to do it in a different order than me. You don't have to do it in the order I did, okay? Any questions about that? All right, so the math is not complex, but there's a lot of it. So keep up with it. Now, here's another little tip. Notice that when I did oxygens up here, I wrote out the math. Look, when you try to save on pencil graphite, and then you can't keep up with where things are, it's because you didn't write it down. If you write it down, take a little time to write a little extra note to the side. You know, a lot of times that's all it takes to keep up with things. If you're trying to keep up with everything in your head, and try to do balancing, and try to write an atom inventory when you've never done it before, you're just setting yourself up to fail. So take the time. Write it down as a side equation. Keep up with it that way, okay? It'll help you in the long run. All right, let's do this for homework. Classify and balance these 4 questions. Classify and balance these 4 questions.